Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 58 today and we are discussing about adhesion of viscoelastic spheres. In the last lecture, I discussed that when you have viscoelastic materials, you have got the effect of time because these materials they relax over time and therefore, you have applied some load. The load may be varying with respect to time or you have applied an step load, and as a result because of the relaxation the creep compliance, that is C, that varies with respect to time, and the contact width or contact radius A that also varies with respect to time, and it is given by this relation from which for a linear elastic material we could derive the JKR contact mechanics experiments. So, this is the equation that we derived, and so today I would like to first present one example. So, example is basically a step change, but before that let me discuss that how to calculate this creep compliance. So, it is basically done by what is known as this stress relaxation test. So, you have this viscoelastic material, you apply a constant shear strain. So, you have this between two parallel plates, this material, and keeping this plate fixed, you apply a shear strain, a constant shear strain is applied, and time dependent decay of the shear stress, that is say sigma z or sigma xz. So, that is actually measured. This varies with respect to time, and we have applied a given shear strain, and the ratio of time dependent stress to the applied strain is calculated to obtain the stress relaxation modulus. And so, here is some data of the stress relaxation modulus, and as you see it varies over 1 to about 4 to 5 orders of magnitude time in seconds, let us say, and from this data we can obtain the GT. So, that is actually the stress relaxation modulus, and then one can obtain from that, let us say the inverse of that, the creep compliance, and creep compliance data can be fitted with respect to time by this kind of equation where the constant m, exponent m, that can be obtained. And then this kind of materials one can do this kind of experiments. So, here basically there is this balance, showing balance for measuring a very small load, and you have these hemispheres between kept on this surface, and the bottom hemisphere. From the top hemisphere using a motorized stage, one applies load, compressive load or pull off load, and one measures the contact radius by using this optical microscope. The whole thing is kept on a vibrationless table, and then one of course sees that with respect to time how the load changes and all that. So, this is one such example. There can be many other example of experiments, but I just wanted to give you a feel of the experiments that is done. So, let us say there is a step displacement that is done at time t is equal to 0. So, what it means is that at time t is equal to 0, one brings this top hemisphere, let us say, and it applies some load some distance. So, this is in essence a displacement control experiment in which the load is measured. So, you give in some amount of displacement and then the load is measured. So, this displacement remains constant. So, it is given something like this. So, delta 0 remains constant. Now, delta 0 can be given as can be related to the A, that is the contact radius by this equation. So, A square by r minus pi into B1, and we have derived this equation in the last lecture, and then we have also derived this relation that B1 as a function of t goes as C0, the instantaneous compliance, and then Ki the stress intensity factor, and square root of A over pi. So, here you substitute this B1 this expression and you get this expression. From there you can do little algebra, can obtain this C0 into Ki. So, by C0 into Ki, okay, simply comes from this equation, and it is given by like this. So, remember that we need a model for measuring the stress intensity factor, and that is exactly what was done in the last lecture, and there we wrote this kind of model where this constant not constant, the variable z had to be measured, had to be estimated, and for that we now have the expression for C0 and Ki, and work of adhesion we know. So, therefore, z here can be obtained as 1 by 2 C0 W m, and this is a square by t and r square root of pi and a here minus delta 0 by square root of pi and square root of a is of course function of t, and this is square. So, here it goes as 1 by 2 C0 and square root of pi is square. So, I think I can take it out, pi W a, and then here it will be a to the power 3 by 2 t by r, and minus this is delta 0 by square root of a to the power 1 by 2 t, like this. So, this is the expression for z, and if you remember that we had some relation of z with respect to some quantity called lambda z and all that. So, we can have all that. We can substitute that expression here. There should be rate, actually this is dA by dt, dm by dt, and like that. So, this z expression can be written on this expression. This also I had presented in lecture 57, and from there you get an expression of dA by dt as a function of a. Now, here the expression for lambda z, Cm, all these are given in the last lecture. Please have a look at that, it is there. So, here now we have the expression for this differential equation with respect to time, dA by dt is equal to this function of phi of a. Of course, this is quite an involved quantity, and one can only solve this using numerical methods, but for that you need the initial condition, and here what I am saying is this initial condition can be obtained by Zeker analysis, because at time t is equal to 0, okay, the step input has been given. So, delta 0 has been given, and so therefore, by solving this equation, okay, at time t is equal to 0 you can use this ky is equal to square root of 2 pi into 2 EA into work of adhesion, that can be obtained, that you can use this elastic limit equation, okay, this elastic limit whatever equation, okay, you can use, and from there by solving this equation you can get the values of A at time t is equal to 0. Okay. So, that has to be the initial condition for solving this problem. So, that can be done, and the problem now needs to be solved numerically. So, of course, that is the more involved and one can do, and the more detail about this methods and all these ideas you can see it in paper and many more other papers. I have just tried to give you some introduction to this problems, this very involved and very rich in physics problem, which is this viscoelastic materials, addition of viscoelastic materials. There is one thing that also one needs to remember here, that we have in this particular example that I showed to you, here I have said that we have given a step displacement at time t is equal to 0, but one can also have a rate dependent aspect. So, the load applied with respect to time. So, that also can be done. So, there are like whenever we have these viscoelastic materials in adhesion, you need to consider also the rate effect. So, something that I have not talked about in this course, but is there, and more advanced level course or some other future time maybe I will talk about that. So, I will now shift to another very important and interesting problem in adhesion with these soft adhesives, and it is about adhesion on rough surfaces, okay, which are decorated with asperities. So, we have talked about all this time about adhesion on smooth surfaces, okay, something like this, or let us say another surface, another surface, okay, which is also, so these are all smooth surface. So, what it means is that if I think that this is the contact radius or contact area, then this is optically smooth. So, it is actually the contact area, but most cases it is not, because the surface is decorated with asperities. So, there are asperities in all surfaces, okay, surface roughness is there. So, how that roughness affects adhesion, and it actually affects quite profoundly. Okay. So, even very small amount of asperity that can decrease the adhesion quite significantly. So, when there is a little hard solid, the solid may be smooth, but then no adhesion or poor adhesion occurs when there is asperities present. However, if the solid is not so hard, it is somewhat smooth, then adhesion can be quite fine. In fact, adhesion might in fact increase with respect to what is observed with a smooth surface, that is also possible. Okay. The adhesive force can actually deform the materials and thereby increase the area of contact. So, that is possible. So, adhesion, it seems it is sensitive to both modulus, we have already discussed about a lot on this, but in addition to that it is also sensitive to surface roughness, and in other ways that adhesion is sensitive to surface roughness and coupled effect of surface roughness and modulus. Okay. It is just not that only surface roughness, but modulus is also important, because as I said that in some situations adhesion might actually increase because of roughness, but in most cases adhesion decreases. So, here is an experimental result that was presented in this paper. So, very systematically done adhesion experiment. I think it is one of the first studies that was done by Fuller and Tabor in 1975, and so they have this rubber surface, rubber spheres of different diameters and smooth, optically smooth, and they bring in contact with perspex surfaces. Perspex surfaces can be flat, smooth, but also can be roughened. So, they actually roughened it to different degree and then obtained the pull of load, and then you can see that depending on the modulus of this material, okay, the pull of load that varies, that decreases quite significantly with even small increase in this asperity. So, they varied also the radius of the spheres and of course, the modulus as I already said, but there was no viscoelasticity in it. So, that is one thing, that there is no viscoelasticity in this problem. We want to analyze such a problem in the elastic limit. So, here the issue is something like this, is that you have got this surface, on this surface you have got this asperities, of course, all different type of length scales and height and like that. And if you really look at, you will see that there are asperities which are of this particular length scale, and then if you look at magnify it further in this region, you will once again see some roughness. So, there are roughness is not in just one length scale, roughness in multiple length scale, but this handling this problem and considering all the roughnesses, all these length scales, and is not going to be easy to begin with. Okay. So, therefore, in here what Tabor and Fuller and Tabor they thought about is that they considered ideal situation in which they have got this smooth surface is the plane of mean asperity height they are saying, but it is basically the datum surface, and on that there are these asperities, and then these asperities have different heights. So, different height can be, okay, which is good, but then they considered that the asperities have the spherical cap of constant radius. So, that means all these asperities have the same radius of curvature over here. Okay. So, asperities may be different in height, okay, but then the radius of curvature is same, that is what it means. So, now this particular surface is can be brought in contact from the top, one contact, one adherent which is smooth, okay, and then one is to see that how many such asperities come in contact with this. So, this asperities, as I said, their height varies. So, there has to be a distribution that can describe this variation in height of this asperities, and let us say that the height of asperity, probability of that height of an asperity is between z and z plus dz, okay, that is given by this kind of Gaussian height distribution which is expressed here. So, here the mean is of course 0, and so the z is the height, and then for this phi z defines the fraction of those asperities which has the height between z and z plus dz, and this sigma s is the standard deviation. So, higher the standard deviation means that larger is the difference between the different heights, okay, of this larger is the width of the distribution in a sense. So, it is like that. So, now what happens is that we bring in contact a flat surface and we consider only frictionless and elastic contact. And so, here let us say that the D is the gap between this datum surface and this contacting plane or contacting flat surface, and so Z is the height of this asperity. So, there is a probability or chance that this asperity will come in contact with this adherent, okay, when its height Z is greater than equal to D. So, if the D is the distance between this quantity between this datum surface, okay, and this surface, then obviously the Z has to be either equal to D or more than D in order that this surface remains or this asperity remains in contact with this adherent. So, if its height is Z is larger than D, then it means that this asperity is being compressed. Okay. On the other hand, if Z is just equal to D, then it is just touching on the surface, that is all it means. So, in general what will be done is that this flat surface adherent, that will be brought in contact with this asperities and then it will be pressed down. Okay. So, as we press down, now what happens is that more asperities come in contact because the gap decreases. So, now more asperities even smaller than this height D, okay, that also now gets in common contact with this surface, and then you try to pull it off. Okay. So, the adhesion needs to consider this aspect, that therefore, in this kind of problem, okay, it matters that how much load you have applied, to what extent you have compressed this adhesive. So, many often you will see that if you do not apply the adhesive very strong enough, then of course, the the adhesion will be weak, and that is because that this asperity, the gap between the asperities that has not been filled in, or the asperities has not come in contact completely with this adherent surfaces and all. So, here in order to take into account, of course, this is a theoretical thought experiment which is being done here, that when you press it more than of course, this quantity D here, let us say, to the extent that more number of asperities now come in contact. So, this contact between this asperity and the top surface, that can be described by using this JKR model that we have done earlier. So, here it is the Hertz model that we have done, and we presented this thing in a previous lecture, I think 2021, 22, 23 and like that, and this is of course JKR model. Now, so we want to find it out from here is that because of this, so this is for a single asperity, by the way, that we have applied the compressive load, let us say P0, and then there is a contact width that forms, that is A1 in presence of adhesion. So, we try to find out the relation between them, and in essence what we are trying to do is that finding a relation between of course, this A and P and like that. So, we in the lecture 23, I was saying that we derived this expression. So, here let us say that we apply this P0 amount of load, and if it is only Hertz contact, then the contact radius will be up to A0. However, there is not Hertz contact, there is also an adhesion between them, and that we have taken care of, that we took care of, if you remember, that we considered that there is a fictitious load P1 is applied, and so this contact width now goes to A1, and then of course, the load is not P1 because it is there is work of adhesion there, and so therefore, keeping at the same constant A1, the load decreases. So, the load goes from here and then it goes to here, this is the path that it follows, and as far as the delta is concerned, so the delta follows this path, it goes over here and then it decreases to some intermediate value over here. So, the final delta or the distance through which the load has moved is this quantity. So, that we have discussed earlier also, that this is the quantity if there was only Hertz Hertz mechanics, in order to have this A1 amount of contact width, okay, it had to give this much amount of displacement of the load had to be there, but no, that is not the case, because we are applying smaller load, P0 amount of load, and there is work of adhesion. So, this P0 load that moves only this much distance. Now, applying that Hertz theory, one can actually get the relation here between P1 and A1, and where capital K we know that this is an elastic constant. So, it given us 4 E star by 3. So, that we have done in the previously. So, here this is the relation between delta and this. So, here I will like to express P1 in terms of this Ka1 cube by R. So, this will be equal to, so P1, so Ka1 cube by R, this is 2 by 3 and K to the power 2 by 3 R to the power 1 upon 3 minus 2 by 3, and then P1 will be Ka1 cube by R minus P0 by Ka1. So, this is will be equal to this here it is. So, K to the power 1 by 3, K to the 2 by 3, so K gets cancelled. So, here it is A square. So, it is A1 square and R to the power 1 by 3, 2 by 3, so it is R over here, okay, and minus here it is 2 by 3 and this K1. So, here it is let us say that yeah, let us keep it like this. So, K A1 cube by R minus P0 by Ka1. So, one can further write, one can further open up all these terms, and one can get here. So, here one can get A1 square by R minus, so it is 2 by 3 and then K, so it is A1 square by R and plus this is 2 by 3 and then P by Ka1, P0 by K1. So, one can get something like this finally. So, we have already gotten something like that. Now, so we can get rid of the subscripts over here. So, I get 1 by 3 Ka into Ka cube plus 2 Pr like that. So, it is the P amount of load that is being applied. So, subscript is important because we are already considering adhesion is there. So, that is why subscript is no longer important. So, this is the contact radius A that is attained when the load P is applied. Now, there is a characteristic load and the characteristic deformation. So, characteristic load can be the pool of load. So, that is let us say Pc, it is 3 by 2 Wa pi and R, and then there is this delta C. So, delta C is given as 1 by 3 R and this is 3 R Pc by K to the power 2 by 3. So, that is the maximum extension of the tip of the asperity above is undeformed height. So, basically what it means is that this tip is there and then this plate from the top is there. So, now they are in contact and now you are trying to pull it off. So, before this tip and this plate they debond, the amount of extension, okay, that happens. So, that amount of extension happens. So, that is this delta C basically. So, this delta by delta C that can be written as, so this is delta C, okay, 1 by 3 Ka R and this is Ka cube plus 2 P R and divided by 1 upon 3 R and this is 3 R P C by K 2 by 3. So, here 1 upon 3 R, so that gets cancelled. So, we have 1 upon Ka, so this is Ka cube by Ka because 1 upon 3 R that gets cancelled over here, and we also have here 3 R P C by capital K by 2 by 3 plus this is, so this is 2 P R by 3 R P C by K by 2 by 3. Yeah. So, in essence what we are going to do is something like this. So, here finally that we obtain here like this K A cube here P by PC. So, everything in terms of this P by PC here and then K A cube here like this. So, this delta by delta C, okay, after we write it over here, it comes out to be something like this. So, this is JKR model equation. So, in this JKR model equation we substitute this PC is equal to 3 by 2 WA pi r. So, therefore, this A1 A cube will be obtained as r by k, and this will be capital P plus. So, this is 3 WA pi r is equal to 2 PC. So, it is 2 PC over here and plus this is square root, again this is 2 into 2. So, it will be 4 WA 3 2 so 3 so 2 this is 4 and this is P into PC. So, 2 PC into P over here. So, it is for 4 P for PC, that is fine, plus this is 3. So, this is 2 PC whole square yeah, like this. So, this is equal to R by K and this is P plus 2 PC, okay, plus this is comes out to be 4 PC into PPC plus 4 PC square. So, one can further write it, it can be written as R by K and this is P plus PC square root, yeah. So, it is P plus PC square root, okay, whole square plus this is square root of PC, okay, square root square, okay. So, this becomes this, okay. So, this is fine and this is 2 here and square root of PC. So, it is PC and square root of this is P plus PC. So, you see this is okay. So, therefore, this quantity will be written as R by K and here it is square root of P plus PC plus square root of PC. So, and square here. So, that way it has been written. So, this JKR model equations using that we get this particular expression, and finally, we have K cube can be written as something like this, and we can further substitute this expression. So, on this Ku cube we substitute the square root of 1 plus P by PC as the psi, and so therefore, Ku cube is this equation, and finally, we have this particular equation. So, P by PC is like this. So, now we can replace substitute for P by PC is equal to psi plus 1 into psi minus 1 and then Ku K cube is equal to this quantity. So, if you do that, okay, substitute that, we get by after sum algebra this particular equation. So, we have got everything in terms of this psi plus 1 psi minus 1 and like that. So, in essence what we have, invert this relations, okay. So, this basically is an expression, is a function of this P by PC. So, in essence what we have, this P by PC is a function of delta by delta C, okay. So, that is what we also obtained. So, now what we need to do is to find out that what fraction of this asperities that will come in contact with this top surface for a given delta, and then what will be the total pull of load that is required. So, I will stop here today, but I will continue this discussion in the next lecture. Thank you.